Let's go through the solutions for the C2 reflection, where you learned about the empirical rule and the normal distribution. So which of the following are true statements? The area under a normal curve is always equal to 1. That does say 1, by the way, no matter what the mean and standard deviation are. 2, the smaller standard deviation of a normal curve, the higher and narrower the graph. Number 3, normal curves with different means are centered around different numbers. So I'm going to use Staplet to explore this. I really like using Staplet to visualize the normal distribution, and you can find it in the second section, probability, normal distributions. And our default curve is a mean of 0 and a standard deviation of 1. What this gives us is a plot with just z-scores on it. And we're going to calculate the area between two values, and I'm going to use a really big number, negative 1,000 to 1,000, and you can see that the area is roughly 1, and it should be 1. If I went to negative infinity to positive infinity, it would be 1. Now, the question is, what if I change the mean? So if I shift the mean and calculate the area, it's still 1, right? And if I change the standard deviation, so shifting the mean just moves that center point. So we went from 0 to 2 to 5. But the shape here is always the same. So number 3, normal curves with different means are centered around different numbers, is correct. All right. Now, let me put it back at 0 for the moment. And the reason we have 0 and 1 is if you're at average, 0 is 0 standard deviations above the average and below the average. It's right at the average. So, but let's try and use some different standard deviations. Let's say a standard deviation of 10. So the only thing I have to be careful about is making sure these numbers are big enough. If I'm going to check if the area is 1, and they are, they're pretty far away. You want to be at least more than 3, ideally like 6 or 10 standard deviations away, which I am. I'm actually like 100 away, which is why I'm getting an area of 1. So statement 1 is also true, that the area under a normal curve is always equal to 1, no matter what the mean and standard deviation are. And now you might be saying, well, what about the smaller the standard deviation, the taller the curve? It's kind of hard to tell here. I'm going to go to a small standard deviation because this automatically scales this way. But you can see that it doesn't take as long. So I'm going to put 10 here. This one is a wider curve because it's negative 30 to 30. So if I were to, so this would look flatter. And if I were to put a smaller standard deviation, I would have more of the curve between negative 1.5 and 1.5 in this case. Or if I just had the regular one, negative 3 to 3. And so these would actually look taller and steeper, higher and narrower. So that statement is also true. So all 3 statements are true for the normal distribution. So now that we've gone through it, we can see that all 3 statements are true. So we select D, 1, 2, and 3. Now we're coming to another question about true statements with a normal curve. So we have the area under the standard normal curve between 0 and 2 is twice. That should say twice. The area between 0 and 1. The area under the standard normal curve between 0 and 2 is half the area between negative 2 and 2. For the standard normal curve, the interquartile range is approximately 3. For the standard normal curve, approximately 1 out of 1,000 values are greater than those with a z-score of 10. And finally, the empirical rule applies only to normal curves where the mean and standard deviation are known. So again, I'm going to go ahead and explore this with Staplet. So I'm going to use Staplet again to explore the normal distribution. And it says the area under the normal curve between 0 and 2 is twice instead of thrice, hopefully. So let me go ahead and put in the area. And I have like the regular standard normal curve, which is a mean of 0 and a standard deviation of 1. It should look like that template that I drew where you have 0, 1, 2, 3, and then negative 1, negative 2, negative 3. So if I calculate the area here, I get 0.4772 from 0 to 2. Is that twice the area of 0 to 1? So remember, that's 0.4772. No, that's actually, you can even see it when this is definitely more than half of the 0 to 2 area. So the first statement is incorrect. The area from 0 to 2 is half the area from negative 2 to 2. So here's 0 to 2, 0.4772. And I'll put in negative 2. And you can see that that actually is half. That kind of makes sense. So again, so here's the whole area, 0.9545, and you can see it's shaded. And when I change it to 0, it cuts it in half. So statement B appears to be correct. For the standard normal curve, the interquartile range is approximately 3. Well, technically, I can find that. This is really kind of jumping into another section. We're going to do central. And remember, the interquartile range is the middle 50% of data. And that goes from negative 0.67 to positive 0.67. That is not 3. And then finally, it's, well, for part D, for the standard normal curve, approximately 1 out of 1,000 values are greater than those with a z-score of 10. So I'm going to put this here. Let me go ahead and calculate an area. And I'm going to go to the right of a value, and I'm putting a z-score of 10. It's not even going to show it here. And it's giving me an area of 0. If it was 1 out of 1,000, I'll tell you what the z-score is for that, just in case you're interested. 1 out of 1,000 is 0.001 for an area. And that's a not central, right tail. There we go. It's a z-score of just a little over 3. So it's just over here. You can barely see it, just in case you're interested. And then I'll go ahead and go back to the slide for the empirical rule. So we found out that so far B is true. And let's go ahead and pull up the drawing for the empirical rule. Technically, the reason I have this drawing blank is because I can have any mean or standard deviation, and I need to fill those in. And I'm able to draw it even though I don't know the mean and the standard deviation, because we know the general shape of it. So that is false. So the correct answer is B. The area under the standard normal curve between 0 and 2 is half the area between negative 2 and 2. Number 3. A piece of clothing takes an average of 38 minutes to move through an assembly line. If the standard deviation is 4 minutes and the distribution is normal, what is the probability that a piece of clothing will take over 45 minutes? So this is something that you shared from prior years, trying to put the lessons for C2. So this was the first one that people really struggled with. So first of all, I'm going to go ahead and draw the model, which is the empirical rule. And I'm going to draw the model unstandardized. What that means is I'm using the actual mean of 38 and the actual standard deviation of 4, and I'm starting to fill in the curve. Now I can tell that 45 minutes starts just before 46, so I can actually estimate that. Here, let me get my laser pointer. So I can actually just estimate that it's roughly this area, but a little bit more because it's starting before that curve. So I'm estimating it to be a little more than 2.5%. The z-score is 1.75. And if I draw that on the standardized curve, you can see that it's just a little bit before 2 standard deviations and up. And we want there's a table you can refer to, an area left of z is 0.9599, because the table, if you use that, always gives left area. But we want area to the right, so I have to subtract that from 1. So for full credit, when you're doing these kinds of problems where I'm grading a quiz or a test, show me the standardized and unstandardized picks with labels. Show me your z-score formula, your work, your z-score, and your final answer. Now, I'm also going to show you how to do this a much easier way with Staplet, but I still expect you to be doing all of these steps for full credit when work is required. So your correct answer is 0.040, and let's go to Staplet. Now, there are multiple ways of solving this. You can use a table, you can use the calculator, but for right now, I'd like you to actually use Staplet because you can see the whole picture and what's going on. So we did calculate a z-score of 1.75, and we want that, so we're trying to calculate an area under the normal curve to the right of a z-score of 1.75. And you notice I have the 0 and 1. Why do I have the 0 and 1? Because I'm using standard deviation, z-scores, and this is always the curve when using z-scores. So I get an area of 0.0401. Now, one thing you're really going to like is I don't have to actually use the z-score. There are times you have to work in z-scores, so don't think you can totally blow them off. But it is possible using the mean and the standard deviation and the actual value. What is the probability it takes over 45 minutes? And then you calculate it, and there you go. So you can see this is a normal distribution that's unstandardized, that has a 38 at the center, 45 minutes and higher to the right, and your area is 0.0401. So again, a much easier way to calculate your probabilities. The SAT math scores for applicants to a particular engineering school are normally distributed with a mean of 680 and a standard deviation of 35. Suppose that only applicants with scores above 700 are considered for admission. I'm going to actually ignore this part of the question for right now, and we might revisit something like this in the future. I'm going to just say what percentage of the applicants have scores below 750 using the empirical rule. So again, we'll need the empirical rule, which is right here. And if I do the unstandardized model, I do 680, 750, and 750. So I get 2 standard deviations and below. So it's probably easier to subtract this out from 1 or 100%. And I get 97.5. So 97.5 is my answer, all right? And here it is standardized. So estimate is more than 95%. There's my z-score. And the correct answer on here, I don't have it circled or showing up, but it is 97.5. It's E. Mr. Rothery administered a self-concept test to a group of 78 students at Perry High School that measured how they felt about themselves. Higher scores indicated more positive self-concepts. A histogram and some summary stats from Minitab for these students' self-concept scores are given below. So this is free response, and I give you full credit for a reasonable attempt, and I'm going over the answers. So worst case, copy off of me, okay? So I really struggled with question 6. I found the z-score, but I didn't know how to find the best measure of data for the center point. Calculating the percentile z-score for a histogram is difficult since the bins weren't very specific. Well, here's the trick. Do you see all of this? These are statistics. So you have mean, you have standard deviation, that's SC is standard error as well. And we have Q1, we have Q3. So we have a lot of information here, more than you think. So first of all, because 33 students, and we did have to estimate, had self-concept scores higher than a 62. Let's see. How did we know that we had more than 33? Well, we said 78 measured how they felt about themselves minus the 33. So, we just counted these 33 higher than a 62. So we must have counted right here. 65. So you got about 16, and then you have roughly, so it's a little bit hard to estimate this. I can see that. And so we had 45 students that had concept scores of 62 or less. Oh, how do I know this? Because part A says so. 33 students had self-concept scores higher than 62. Helps to read the question. And 1 student in the group had a score of 62. So that one student is actually going to go in the lower pile. So we have 45 students below 62, and 45 out of 78 is 57.7, which puts them at the 57.7th percentile. Now, if I want to calculate z-score, I need mean and I need standard deviation. So how do we get 0.42? Well, what I'm going to do, actually, does this have z-score? No. So I'm going to basically take 62 minus 56.85 and divide it by 12.35. So let me go ahead and write that down. For some reason, I don't have it. So pointer options pen. So I'm going to say 56.85. Excuse my mouse writing. Minus, actually it's minus the mean. It's your data point minus the mean. Ignore this. This is not part of it. 62, so we're going to have a positive z-score because we're above average. And so that's roughly, not quite 6, right? It's close to 6. And we're dividing by 1.4, and you will find that one student in the group had his calculate and interpret. Oh, I have the wrong standard deviation. I had standard error. Sorry. We have standard deviation right here. 12.35. So 6 divided by 12.35 is a little less than a half. There's your standard deviation. There's your mean. That's what you were supposed to use along with this value to find the z-score. All right. So that's how you get 0.42. It's a positive score. So this student's self-concept score is 0.42 standard deviations above the mean. Now, what value is the best measure of the center for the distribution of self-concept scores for these students? Well, this data is skewed left. And when data is skewed, we avoid the mean. All right. We don't like the mean. Mean bad. We like the median. The median is preferred. So 59 is the best measure. I'm going to switch back to my laser pointer. If this number 6, if the standard deviation of a set of observations is 0, you can conclude. And well, a standard deviation of 0 means the spread is 0. So then all observations have to have the same value. So that's true. It also doesn't affect the mean, so that's false. And it doesn't imply that there is no relationship, or there is, or that there was a mistake in math. So the correct answer is C for number 6. On to number 7. This tends to be a pretty tricky one. Given the probabilities, probability A is 0.3, probability of A or B is 0.7. What is the probability of B if A and B are mutually exclusive? And then redo the problem if A and B are independent. By the way, mutually exclusive and independent don't happen together, just letting you know. All right, so first of all, I'm going to look at the probability of A or B from the formula chart. And if they're mutually exclusive, that means the probability of A and B is 0. So I'm just going to substitute in all my numbers. 0.7 equals 0.3 plus probability of B minus 0. So I get 0.4 as the probability of B. So my answer is either A or B. And then, hopefully I have the right one circled, if A and B are independent, then the probability of A and B is the same as probability of A given B. All right, so, but the thing is, I don't know probability of B, so I'm going to substitute back into the same formula, same exact formula, except now I know that this is supposed to be true if they're independent. And I substitute in all the values I know. I have 1 probability of B minus 0.3 probabilities of B, that's 0.7. And then I move the 0.3 over here, so 0.4 divided by 0.7 is the same as 4/7. So my correct answer is, it's going to be this 0.4 and that 4/7. So again, you have to really understand what mutually exclusive means, what independent means, and you have to be able to use the formula. Given the 2 histograms below of relative frequencies, which of the following statements is incorrect? So I'll start, I'm just going to kind of go in different orders. Let's say we start with the range. Both sets have a range of 50 minus 10 because range is max minus min, so that one's true. The median is 30 for both sets because that is the halfway point between data. That's true. And the mean, because they're symmetric, the mean and the median are exactly the same. So it's 30 for both sets. That's true. Then it says set A has a greater variance than set B. Well, variance is a measure of spread. It's just standard deviation squared. So definitely more spread here than there is here. So that's true. So we don't have a vertical scale, so we don't know that there are exactly 12 data points. It's E that is false. So E is the incorrect statement. Always pay attention if they're asking for incorrect or correct. Very helpful to mark your truths and your false as you go along. All right, then number 9. In one large city, 40% of all households own a dog, 32% own a cat, and 18% own both. Suppose we randomly select a household and learn that the household owns a cat. Find the probability the household owns a dog as well. So I'm going to start with the Venn diagram because we do have overlap between cats and dogs. And you don't want to start with the 40% or the 30% because that's like the bigger circles, but the 18% that own both, we can totally do that. So first circle is dogs, second circle is cats, 18% goes in between. So I can figure out what percent own dogs, but not cats. That would be 22% because I take that 18 out of the, should be 18 out of the 40. Let me go ahead and fix that. Sorry. How did we do that? So it would be 40 minus 18. Oh, I had the right answer. I just did 42 for some reason. Who knows? So here we go. It's 40 minus 18, which is 22%. And then I'm going to take the 32% here and subtract the 18, and I get 14%. Now, this didn't really affect my answer. It's fine. So probability of a dog given a cat is the same as probability of a dog and cat, which we said was 18%, 0.18, over the probability of having a cat. And we knew the total for that was 32% or 0.32. When we divide it, we get 0.5625, which rounds out to answer E. Problems 10 through 12, airport security. The Transportation Security Administration, TSA, is responsible for airport safety. On some flights, TSA officers randomly select passengers for an extra security check prior to boarding. One such flight had 76 passengers, 12 in first class and 64 in coach. Some passengers were surprised when none of the 10 passengers chosen for screening were seated in first class. We want to perform a simulation to estimate the probability that no first-class passengers would be chosen in a truly random selection. So how would you use a table of random digits to carry out this simulation? First of all, I'm skipping A because it says none of them are right. So we're going to see if we find one right, and if we don't, A must be the choice. So number the first-class passengers from 1 to 12, and the other passengers 13 to 76. Ignore all other numbers. So you need to specify 2 digits. And ignore all other numbers is fine. I personally like to list them out. We would be ignoring 77 through 99 and 00. So B won't work because it looks like it could be single digits or 2 digits. And it doesn't really specify digits. So bad plan for a random number table. C. Number the first class passengers from 0 to 12. See, this is doing much better. And the other passengers 13 to 76. Ignore all other numbers. So we can live with that. Moving left to right across the row, look at a pairs of digits until you have 10 numbers. The problem with this, it did not specify to ignore repeats. You need to tell me what to do with repeats. And so this one's wrong, okay, because we did not talk about repeats. Choice D, 0 to 12 and 13 to 76 looks good. Looking at left to right across the row, look at pair of digits until you have 10 unique numbers. This is nice. This is beautiful here, all right? Then count the number of 2-digit numbers between 01 and 02 and determine how many have been selected. This would be great for running one trial, but we actually need to multiply this out and not multiply, but run many trials if we want a simulation to figure out a probability. Choice E. So we have the same beginning. The next part, no reps, pairs of digits. Count the number of 2-digit numbers between 01 and 02. Perform many trials and determine what percent of the trials showed no first-class passengers selected for screening. We like this one. It defined the outcomes. It ignores repeats. It reports the number of first-class passengers, and it performs many trials. So the correct answer is E. We don't even have to look at A. So now we're going to go ahead and do a simulation pretty much saying what we did before, but we're just going to do one trial. So we're not doing a full simulation. So you can see it says one trial using the random digits. So what I'm going to do is I'm going to pair off these numbers and then show you what's going on. 71 is regular, 48 is regular, 70 is regular. So you can see 71, 48, 70. 99 we ignore, 84 we ignore. So these do not count towards my 10-person passenger count. Then we've got 29 is regular, 7 is first class, 71 is ignore because I already have a 71 right here. It's a repeat. 48 we also have. That's a repeat. Then 63, 61, 68, 34 are regular. Oh, we got another repeat. And then finally we got a regular, and we finally reached 10 passengers. So how many first class passengers do we get? Just that one. Our answer is C. In 15 of the 100 trials of the simulation, none of the 10 passengers chosen were seated in first class. Does this result provide convincing evidence that the TSA officers did not carry out a truly random selection? Why or why not? So 15 out of 100, the simulations were based on the fact that all were equally likely. So our claim is that it was random. Our assumption is that it's truly random, that first class passengers weren't preferentially not pooled, right? That you weren't more likely to get picked if you were in coach. So based on these simulations where everyone was equally likely, we had 15 out of 100 had no first class passengers. 15 out of 100 is 15%, and we do not consider that unusual. So definitely there is not convincing evidence. And both of these start with the same sentence. There's not convincing evidence that TSA officers did not carry out a truly random selection. This says 0% chance. That's not correct. If the selection is truly random, there's a 15% chance that no one in first class will be selected. So we're not surprised. So the correct answer here is B. Number 13. We used an online growth chart to find percentiles for the height and weight of a 16-year-old girl who is 66 inches tall and weighs 118 pounds. According to the chart, this girl is at the 48th percentile for weight and the 78th percentile for height. So what does this mean in plain English? So 48th percentile means that she weighs more than 48% of girls according to her chart. So 48% weigh less than or equal to her weight, right? And 78% are less than or equal to her height. And that fits choice A, number 13. Now, on to superpowers. A random sample of children from 415 children from England and the U.S. who completed a survey in the recent year was selected. Each student's country of origin was recorded along with which superpower they would most like to have: the ability to fly, the ability to freeze time, invisibility, super strength, or telepathy. The data are summarized in the two-way table. Suppose we randomly select one of these students. So E is England, T is telepathy, and S is super strength. I think I used SS, but it's no biggie. All right, so find P of T given E. So find the probability of telepathy given England, and then interpret this value in context. So first of all, given means it's in England. We ignore everybody else. All the U.S. kids, sorry, we're ignoring you, all right? So we're trying to find the probability of telepathy given they're in England. So we take the number that chose telepathy and are in England, that's 44, and that would be these 44 right here, out of the total number from England, which is 200, so we get 0.22. So the only difference between these two, they have the same answer. One says given the student is from England, the other one says given the student selected telepathy. We were given that they were from England, so that's how we know to interpret that. Given that the student is from England, there's a 0.22 probability that they selected the superpower of telepathy. I don't know, which one would I do? I'm not sure. Okay, given that the student did not choose super strength, all right, so we ignore all other students who chose super strength. Actually, I should change that. Let me say, get my pen. I meant who Ignore all students who chose super strength. All right. And that's chose super strength. By the way, none of them have super strength, so I wonder why I wrote that. Okay, so ignore all students who chose super strength, and that's why I crossed out the line there. Get back to my laser pointer. And so I'm going to do, let's see, I am going to do this. Actually, let me just fix this real quick since we're on it, and I have to fix one other thing anyways. So there we go. Let me fix that phrasing. Ignore all students who chose super strength. There we go. Chose. There we go. And you can ignore my lines here. So ignore all students who chose super strength. And so we ignore them here. And so we have the probability of England given not super strength. So that would be England and not super strength. So England is 200 kids, and we just want people that didn't choose super strength. I'm taking away the 20. I could have added 54, 52, 30, and 44, but that's the same thing as 200 minus 20. So I'm saving a little extra time. And then the total for everyone that did not pick super strength, so I just subtracted these 43 from the 415. I get 180 over 372, which is 0.48. So that is the correct answer. And that's it for your reflection problems.